Now PPT is visible.
Yes, sir.
Okay. Yeah, in the first module, again in that only one questions we covered here. That is simple and compound stresses. As you know that already what do you mean by stress, the types of stresses, then strain, then types of strain, then what is the relation between stress strain. How do you know that? By taking a engineering material, there is a mild steel, low carbon steel, then you go for plot the graph stress versus strain, then you know the stress strain relation within the elastic limit. Okay, then also we studied about Hooke's law, the mechanical properties of materials, then what are the mechanical members and syllabus, right? Those things already we discussed. In last class also we discussed about thermal stresses, right? Yeah, the PPT is visible. The title of the slide is thermal stresses.
Yes, sir.
Okay, so last class we discussed about thermal stresses. When thermal stresses are occurred in a component means if the component is constrained one. Constrained means the ends are restricted, ends will not move, means ends are fixed. Whenever the rise in or fall in temperature of that body, there you can see the thermal stresses. The stresses induced in a constrained body due to rise or fall in temperature of a body, those stresses are called as a thermal stresses. As you see in any machineries or in any structures, one structure is connected to another structure, they leave some gap because due to rise in temperature in the environment, those material undergoes expansion. If you call decrease in temperature in the environment or material, those components undergoes contraction, decrease in dimension. Okay, so there are three cases you consider here thermal stresses. Suppose if the member is in space, there is no constraint here, then if you raise the temperature of the body, what will happen? The body will undergo freely expand, it will increases its dimension. How much is to increase the dimension means delta L is equal to alpha into delta T into L in millimeter. Alpha stands for coefficient of thermal expansion. This is one of the physical property, mechanical sorry, not physical, thermal property called as. In the mechanical, again some subcategories are there, properties that comes under thermal properties, thermal property of a material. Coefficient of thermal expansion, that physically how do you measure here? Millimeters per millimeter per degree centigrade. Now second case here, if the both ends are completely constrained, then due to rise in temperature of a body, what happens? If there is no constraint, it is freely expand. But if its constraints are there, the body is try to expand it, but due to constraint, the body will not deform. What happens from the support to the body? The compressive force is acting over the body. Then it is a thermal stressor developed in a body. That is okay. Third condition, partially constrained means one end of the body is fixed, another end the we give a support at a distance of some gap will maintain here at a distance. Then it called as a partially constrained. These are three cases we'll discuss in the last class, and remember those formula. So for free expansion, delta L is equal to alpha into delta T into L. For completely constrained or restrained, or the thermal stresses are developed, what its magnitude is alpha into delta T into E. Next, partially constrained means there is a gap between one support to the free end of the surface of the bar or a member. That gap we call as a delta, right? Now, what is the stresses developed here? Sigma is equal to alpha into delta T into E minus E into delta whole divided by L in Newton per mm square. And also we solved a simple problem related to thermal stresses. Now one more very important topic for especially for aerospace engineering or mechanical engineering, the term is called as factor of safety. I think this slide is visible.
Yes, sir.
Yes, sir.
Yeah, thank you. Factor of safety. So the indicates here factor of safety for our safely we are go for working on the engineering material or the material can withstand the load. Okay, it has to do its function. Then you go for additionally you go for add it. For example, best example I can give if you take a railway bogies. It may be a passenger train or goods train. Locomotive we take railway bogies. See the what is the thickness the sheet or the body of the railway bogies they maintained here. Why they give more material? Because of for safety purpose, for safety of the human beings, of safety of the passenger. Okay. So the factor of safety shows whenever an uncertainty loads or accident may occur, then what happens? The material will failures to withstand the load. Then how do you avoid that? How do you make it the metal can withstand the load? By giving by giving a factor is called as a factor of safety. So for a physical definition, factor of safety is the ratio of failure stress to the allowable stress. So mathematically you can represent as factor of safety is FOS. Factor of safety is the ratio of failure stress to the allowable stress. Now what is the failure stress means? For example, it depends upon the type of failure occur. If we take a ductile material means low carbon steel, the mild steel, aluminium, copper, those are ductile material means if you apply a load on the material it will continuously deform, right? It continuously deform. So how much deformation takes place here? Okay, if you apply a load continuously deform, then finally it reaches to plastic state, then failure occur. Right? If you apply load on the ductile, if you apply the load on the engineering material, it continuously deform. Then up to elastic limit, if you leave the load, it will come back to original shape and size. Again, if you apply a load, again the material will deform continuously. It reaches to plastic state, plastic region. Plastic region means if you remove the load, the material will not come back to the original shape and size. That we can say the material undergoes a plastic region or plastic state. Okay, if the material is continuously deformed by applying a load, then those materials called as a ductile material. Okay, and another one is brittle material. For brittle material means if you apply a load on the material, that also will undergo a deformation, very small amount of deformation. And once it reaches plastic state, finally it breaks. Okay, that material is called as a brittle material. Brittle materials are cast iron. If other than the metals, if take glass is also brittle material. Okay, if you take cast iron, glass, any other components, but that will not undergo deformation, continuous deformation, large deformation. Small deformation takes place. Again, if you increase the load, the failure occur. Okay, those materials called as a brittle failure. Usually for engineering materials, if failure, the structure or machine members are failures are called as ductile failure and brittle failure. Two commonly occurring failure in structural and machine members are ductile failures and brittle failures. Ductile failure means when you say the metal is reaches to ductile failure means remember the stress strain diagram for mild steel or low carbon steel. Suppose up to elastic limit if you apply a load, then the material is safely withstand the load. Once it crosses the elastic limit, it reaches the plastic limit. Once it reaches the plastic limit, what happens? The failure may occur. We call as the failure may occur. That failure is called as a ductile failure. Okay. See the ductile failures involving excessive deformation extending to plastic stage. What happens brittle material? Brittle material failures occur without significance of a plastic deformation. Then finally the material will failure. That we can see the stress strain diagram for cast iron or other materials. You can see that there is only straight line, then immediately the curve and the failure occur. For ductile material, you can see the straight line up to elastic limit is a straight line, stress versus strain diagram. Then it reaches yield point, upper yield point, lower yield point. Then it goes to a non-linear relation between stress and strain. That is a curve. Then it reaches ultimate point, then breaking point. Okay, so those are the two common failure occurred in structure and machine members. One is ductile failure, another one is brittle failures. Then our engineer's intention is to material will not fail due to an applied load. That in that way you go for design the component. Okay, then how do you design the component means, see that for if it is a ductile materials should always be stressed within the elastic range. Means whatever the load you are applied on the material, that should be within the elastic limit or within the elastic range only you should apply the load. Then only the material is with the standard load and it has to do its function. Suppose if you increase this load, what happens? In order to avoid the ductile material should always be stressed within the elastic range in order to avoid plastic deformation. Then in order to avoid this plastic deformation, within that elastic region only you apply the load. Then we will go for limiting the stress. Thus the limiting the stress which can be induced to yield stress. Means what? If you consider a component is made up of a ductile material, means mild steel or copper, aluminum, bronze, brass, those are the ductile material. If you apply a load on the ductile material, how much load you are going to apply here? Whatever the stresses developed in the material, that should be less than the yield stress. Then the material can withstand that load. Again, if you increase the load, what happens if it reaches yield stress? If it crosses yield stress, then you can say that the material will fail. Once it reaches to plastic region, the material will fail. The ductile material will fail. Then again you go for replace that component. Okay. So you go for limiting the stress which can be induced to yield stress. Okay. Now we consider the failure stress for ductile material is yield stress now. Okay. Next one, the brittle. If you consider brittle materials characterized by small deformation, maybe stresses till ultimate stress, behind which sudden failure may occur. For brittle material, what happens? Stress versus strain diagram, we see that is a linear straight line curve. Once it reaches, if the curve with deviation occur, means curve, instead of straight line, stress versus strain diagram, it is curve suppose occurred. Now immediately it undergoes plastic stage. Without information, the material will fail you. That you can see the cast iron, even in glass also. Okay, behind which sudden failure occur. Now what is the limiting stress for ductile material? Limiting stress for brittle material is not, that is the ultimate stress. Nothing but failure stress is what? Ultimate stress. Yeah, now next slide is visible. Someone has
Yes, sir.
response?
Yes, sir.
Okay, thank you. So now that is a failure stress. We know that for brittle material, for ductile material, we know the failure stress is what? Yield stress. For ductile material, what is the failure stress here? Ultimate stress. Now what will be the allowable stress? It is essential to limit the induced stress to a value which is less than the yield stress in case of ductile material and less than the ultimate stress in case of brittle material. Means we are going to limit the stress, okay, depend upon the material. That suppose if ductile material is there, whatever the stresses you consider here, that should be less than the yield stress. Then the material is safe. Okay. Suppose if it is brittle material is there, what is the limiting stress you consider here? That should be less than the ultimate stress. Thus, limiting stress is referred to as allowable stress, working stress, or is also called as a design stress. When you go for design of aircraft structures, there you can go for determine the design stress or design stress is given. Then you calculate what are the stresses induced due to an external applied load. Those stresses should be less than the design stress, means then it is safe. Okay. Now we'll go for define the factor of safety. It is a ratio of general formula for factor of safety is failure stress to the allowable stress. For if you consider ductile material, what is the failure stress? It is yield stress. Allowable stress, as it is allowable stress only. Now how do you represent here? Yield stress is sigma suffix y whole divided by allowable stress is sigma suffix allowable. For brittle material, failure stress is ultimate stress. Again, allowable stress should be less than the ultimate stress only, or within the less than the below the ultimate stress only. Now factor safety for brittle material is sigma u by sigma allowable. Now So why do you want to give the factor of safety? That is the main important. If sudden the whatever the load is occurred on the component, okay, or the accident occurred, whether the material have to withstand that load or not. If it withstand the load means then it is safe. It is safe to it has to do its work. If sudden applied load or so accident may occur if uncertainty in the load. Best example you can see the in plastic chair. Okay, in plastic chairs, suppose if you sit on the plastic chairs comfortably means if you go for take the chair and sit over that. If suddenly you go for sit on the chairs, what happens? The plastic will not withstand the load, it will failure. Means its factor safety is less. It is. Best example factor safety, if you want to design a component, always take factor safety should be greater than or equal to 1. For engineering materials, factor safety should be greater than 1. What it means for factor safety should be greater than 1 means, if it is greater than 1 means, whatever the yield stress should be far greater than the limiting stress or allowable stress. That's why if yield stress is more means material amount of material which is added over the component is also more. That's why you can see in our country we can see all the machinery components or in vehicles they give the thickness of the body, they will give more because we are taking a more factor of safety, more we are concerned about the more passenger for safety purpose. Again, why do we go for factor safety is greater than 1 for Indian material, for engineering materials that are in India, in our country? Because of whatever the materials we use, engineering materials are used, those materials are not pure material, they are impure materials. How do you say impure material means? Just when you go for conduct the experiments, so first time you go for conduct the experiments, we'll get some value. Same material will go for second time, we'll go for conduct the experiment, we'll get same value you'll get or different value you'll get. Usually it slightly varies the values. Okay. Again, if you take the same component made up of same metal, again you go for conduct the experiment, again you get another value. Slightly changes in the values in that material when you go for conduct the test because of whatever the materials we use, those materials not a pure engineering materials, those are called impure materials. That's why for in India we go for use factor safety always greater than 1. It may be 2, it may be 3 also. For example, if you go for foreign countries, okay, in Germany also they use more than 1. For US, United States, they will use exactly equal to 1. Factor safety equal to, they will use equal to 1 only because of they will save the material. Their material, whatever they use the material, they are pure material, pure engineering material means 99.99% the composition is same. Now if you go for conduct the components, what they are made up of the material, engineering materials, the 99.99% the pure means you will get the same. If you go for different tests you go for, you get the same results. Okay. So if factor safety greater than 1 stands for what? The safety purpose you go, you take more, but the metal consumption is also more. If equal to 1 means metal consumption is less. This is the importance for factor of safety. This is a very important term. Repeatedly, when you go for design the structures, aircraft structures, the term should be there in your in the questions or in that topic. Then you go for determine. Factor safety is a ratio of failure stress by allowable stress. If it is the aircraft structure is made up of ductile material, then we'll go for apply the sigma y by sigma allowable. Now we get sigma y is already we know that. Then calculate factor safety is given that value should be greater than 1. Then calculate what is the limiting stress or allowable stress. Once you get the limiting stress, now then you go for determine whatever the stresses induced in the component due to an external applied load. Those stresses are called as induced stresses. The induced stress should be less than the allowable stress. Then you can say the structure can withstand that load, or else it will failure. Right? Then once it is failure means again you go for change the design parameter. Okay, that we will study in the 4th or 5th, or it may be in 6th semester. Yes. Any doubt regarding this topic, factor of safety? If you have a doubt, you can ask me the question. Unmute yourself. Now remember the general formula for factor safety is the ratio of failure stress to the allowable stress. For yield stress for ductile material, this is the formula you should remember. For brittle material, this is the formula you should remember. Remember always factor safety should be greater than or equal to 1. Usually for Indian engineering materials, you always take greater than 1. Maybe 1, 2, 3, 4, even 7 also we consider. Depend upon the type of the engineering material and depend upon the applications. Yes. Any doubts? Aradhana?
Yes, sir.
Any doubts regarding this factor of safety?
No, sir.
Okay. Shall I move on to the next topic?
Yes, sir.
Okay, thank you. So now, before going to actually, I told you that today I'll go for discuss about stresses acting on inclined plane. Before that, first I will go for list out the formulas and we will go for solve the some question paper problem. Then we will go for discuss the stresses acting on inclined plane. Okay? Yes. So for any problematic subject, if you want to understand thoroughly and you have to make a, for exam point of view, make a good marks if you want to obtain good marks, because in problematic subject you can expect out of out. For 100 marks means 100 marks you can expect, but theory you can't expect 100 out of 100 because there is what they will deduct the marks in the theory subject, but in problematic subject they won't go for deduction marks, because if derivation is there, full derivation, if you do that with assumptions and all the derivation, you get full marks. Even if you go for problems, if you solve the problem, whatever the answers you got that matches with the scheme is, again you get full marks. Okay. Now if you want to solve the problem, before going to solve the problem, first you list out the formulas. Okay, you should list out the formulas and you should remember it. Then only you can go for solve the problems, because data handbook will not give for this subject. You go for designing the structure, there you can see the data handbooks. Already so many formulas are available. Yeah. Now before going to solve the problem, these are the formulas you should remember. So in our subject is a mechanics of material, or is called as the strength of material. In that, what topic we discussed here? Simple stresses and strain. Right. Now this slide is visible.
Yes, sir.
Yes, sir.
Okay, thank you. Now, what is the first formula we used here in this subject, in this module? Whatever the external effects occurred on a component is equal to internal effects. External effect means external force is subjected on the member or a component. What is the internal effects means? First, internally it will resist the force that produces the internal force. Then change in dimension takes place, that we call as a deformation. The internal resistance force occurred over a cross-sectional area, that gives what? Stress. Deformation means change in dimension. If you change in dimension over the original dimension, then that is called as a strain. I think is visible, I don't know, written in the pencil. Okay, here stress,
It's
here
left.
it is strain. Okay, this is the first formula you should remember. Second formula, what is here we know the stress is nothing but intensity of internal resistance force over a cross-sectional area, right? Now there are three types of stresses are there: tensile, compressive, and shear. The tensile and compressive stress is also called as what? Normal stresses, because they are perpendicular to the cross-section here. Means they are acting over along the axis. That's called the normal stress. Normal means perpendicular to the cross-sectional area. The normal stress, it may be tensile or compressive nature. What is the formula for normal stress here? Normal force over by cross-sectional area. Normal stress we represent as sigma. Force we can represent either P or F. Okay. Divided by cross-sectional area is A. Force is in Newton. Cross-sectional area is in millimeter square. Newton per millimeter square. Now in this subject, you should remember always dimension should, what is the unit of dimensions you consider here? Millimeter. What is the dimension of force? It is in Newton. Okay, remember that. Now after the third formula, what we use here? Shear stress. Shear stress is defined as is a ratio of shear force divided by cross surface area, not cross sectional area. Make it correction here. It is not a cross sectional area. What area it is? Surface area. Is a shear force acting over surface area. Now this is a component you see in the camera. This is the bar, rectangular bar it is. This will be the cross sectional area. Section. If you pass an arbitrary cutting plane, what section you will get here? That is a cross section area. This is what? These are the remaining four other sides are surface area. Okay. Now shear stress is equal to shear force divided by surface area. Make it correction here. The shear force is represented as F suffix tau, or you can F also. Surface area is A suffix S you take. That is also in unit is Newton per mm square. Next we discussed about fourth formula, which is the fourth formula we used here, strain. How do you define strain? Change in dimension to the original dimension. What is change in dimension? If you want, you can write here final dimension minus original dimension or initial dimension whole divided by original dimension is nothing but initial dimension. If you want, you can write here also. Then we have three different strains are there. One is the strain occurred along the length of the bar, means along the loading direction, that is called as a longitudinal strain. Longitudinal strain, that is a ratio of change in length by original length. Second one is transverse strain, means if you apply load along the axial direction, length increases. Other two dimension, what happens? Dimension decreases. There is a transverse direction. Transverse strain is defined as change in transverse dimension to the original transverse dimension. If it is circular cross section of the bar, it is diameter will come here, lateral dimension, change in diameter to the original diameter. Then comes to shear strain, means in the shear strain there is no change in dimension takes place. Here in the shear strain, change in shape of the body takes place, that we represent here gamma. You can see that the square shape of the component is converted to a rhombus. How much angle it is converted here? That is angle gamma. That is delta by h. Delta is nothing but it changes its position. For example, okay, 1 minute. I'll show that directly. I'll go to that. The relation between Young's modulus and shear modulus. Yeah, now the slide is visible. Relation between Young's modulus and rigidity modulus, or shear modulus. Yes, give me response.
Yes, sir.
Yeah, now see that here is a square lamina of unit thickness, right? Now if you apply shear load, what happens? B changes to B dash, C changes to C dash. How much angle it changes here? That it will change in shape from square to a rhombus. The gamma is equal to what? This is a tan gamma. If you take tan gamma is equal to opposite by adjacent, means opposite side means C dash divided by adjacent side means if you consider this square lamina, it is H. Height is all dimensions are equal. AB is equal to BC is equal to CD, that is equal to AD, that is equal to H you consider. Now the tan gamma is equal to opposite by hypotenuse, C dash divided by CD. Now C dash is nothing but what? Is a change in, is not deformation, is a displacement recorded, change in position here. That is will represent as delta. Now CD is nothing but H. That is a gamma. Then go for smaller angle. Tan gamma become gamma. Then gamma is equal to what? C dash divided by CD. C dash is nothing but delta. CD is nothing but what we represent as H. That is a formula. You can see that for shear strain. Yes? Any doubt regarding shear strain? Next. Now actually the fifth formula I will not use here. I will not explain here. So what is the fifth formula here? Percentage of increase in length. How much percentage of the length is increases? Nothing but what? Change in dimension here. What is the change in dimension? What is the formula? You have change in dimension means final dimension minus initial dimension. but I need a percentage means you'll go for take a ratio to the initial dimension multiply 100 here. That gives the percentage of increase in length. See the figure here. As you know that for tensile test, okay, a tensile force acting over the component, initial load you have applied here. Now the length is goes on increases, right? Length goes on increases, at the same time diameter decreases. Means here the increase in length here, how much percentage of increase in length here? Final length minus initial length divided by initial length into 100. I think this topic has covered in material science subject. I don't know whether the professor has covered or not. Someone has to give me response. You have material science subject, right?
Material science, no sir.
Aerospace materials.
Yeah,
In
but
that
he
first
haven't.
module, they covered this one.
Not yet, sir. Not a percentage.
Okay. Now you remember this. Or you come to the material testing laboratory. When you go for to conduct the tensile test on the specimen, now we will use this formula. Okay, remember this formula here. At the same time, what happens the diameter or the cross-sectional area? If you if you apply load along the axis, length increases, diameter decreases. Now see the percentage of reduction in area. What is the percentage of reduction in area? What is the reduction in area means? Which area is more? Initial area is more or final area is more? Initial area is more.
Initial.
Yeah, initial area minus final area whole divided by initial area. Multiply 100, that gives a percentage. Now remember these two formula. Okay. Next, after that, now sixth formula, what is that? Engineering stress and engineering strain. Engineering stress, when you go for take engineering is nothing but is a theoretical stress. Means with respect to what cross-sectional area? Original cross-sectional area. So load divided by original cross-sectional area we consider here for engineering stress. For engineering strain, change in length by original length or change in dimension to the original dimension. Instead of that, engineering stress and strain, if you go for true stress and true strain, true stress means see that denominator instantaneous cross-sectional area means at particular time what will be the cross-sectional area is there. First see that for first figure, if I apply a load here, initial length is L1 and initial area is A1. If you apply a load here, what happens? Length increases, right? L1, L2, length increases from L1 to L2, area is decreases from A1 to A2. At that time, instantaneous time, what will be the cross-sectional area that you consider? That is called as a true stress. True stress, and if you for strain also, true stress is nothing but is a load divided by instantaneous cross-sectional area, or instantaneous load by instantaneous cross-sectional area. Instantaneous means at particular time what will be the load is there, what will be the dimension is there, a cross-sectional area is there. Again, true change in gauge length into instantaneous length it is. Again, we see that the formula what we used here, but those formula will not use for calculation purpose. Still, will not have this one. Okay, but again for engineering purpose, which type of stress strain diagram will go for use here? Engineering stress and strain, not the true stress and true strain. Why? Because at each time will not go for measure the what will be the cross-sectional area. What will be the cross-sectional area occurred? For that, what we'll do? We'll take only the original cross-sectional area. For this is what we call as analytical method or theoretical stress strain diagram and theoretical stress and strain formulas. Right? Then after that, what is the seventh formula what we use? You know the stress, you know the strain, and then you go for plot the stress strain diagram. Now we'll get the relation between stress and strain. Within the elastic limit, stress is directly proportional to strain. In order to remove the proportionality, we'll get a constant. Then sigma is equal to E into epsilon. That is what law it states that Hooke's law. It is a one-dimensional Hooke's law we call this because we are applying a load in one direction and also deformation takes place in only one direction. Deformation we consider only in one direction, one axis we consider. That's called the one-dimensional stress strain relationship. What is E? E stands for proportionality constant, or also known as Young's modulus or modulus of elasticity. And next formula what we use here in the engineering mechanical properties of material. The strength is nothing but what? Stress only. Next, stiffness. Second mechanical property, stiffness is nothing but what? Load per deformation. Load is nothing but either represent P or F. Deformation is nothing but delta L. Stiffness we represent as K. What is the unit? Newton per mm. Right. Next, sixth in this eighth one we can use this is a formula used for resilience. The energy stored in a body within the elastic limit or within the elastic region, it becomes a what type of curve it is? A triangular shape. You go for take the stress strain diagram. What is the area of the triangle? Half into base into height. That is the strain energy. Right? That is a resilience. This is a unit for resilience. Now we will not use this formula, but when you go for higher semester, 5th, 6th semester, we have other subject, design related subject, there you can use this formula. And now the next slide is visible. Let's give me a response.
Yes, sir.
Yeah. Next, what
Yes,
is the
sir.
next formula we use here? Toughness. Toughness means ability of material to store the energy in both elastic region and plastic region until it's fracture. That how much amount of energy is stored until it's fracture, that energy is called as a toughness. Right? This is a formula used for toughness. Next, afterwards, next very important now the formulas are, one is you consider a bar, mechanical member or aerostructural member you consider as a bar. Bar is nothing but a member you subject to what type of load? Only axial loads. It may be tensile or compressive in nature. Now here consider a bar. If it is straight bar, uniform cross section bar, what is the deformation of cross section uniform cross section bar? It is, remember this formula, delta L is equal to PL by AE, where P is the external applied load, L is the length of the member, A is the cross section of the member, E is the Young's modulus of the material. What is the unit? Here I missed the unit here. Write down the unit, delta L is equal to PL by AE in millimeter. Similarly, next one, deformation of bar for tapering bar or uniformly varying cross section. If it is circular cross section varying here, delta L is equal to PL by AE. Instead of A, how do you remember A? For tapering bar, it is circular tapering bar pi by 4 D1 into D2 because we have two different diameters. That's why area of the tapered bar, how do you remember here? Pi by 4 D1 into D2. For uniform bar, what is the area is? Pi by 4 D square, right? So throughout the length, the cross section or the diameter is same throughout the length of the bar. Now if it is for a rectangular cross section, for rectangular varying cross section, now this is the formula we use, PL by B1 minus B2 into T into E log E base E B1 by B2. B1 is greater than B2. If it B2 is greater than B1 means now slightly changes the formula. Okay. Next one, deformation due to self-weight. No external force acting on the bar. Here in the previous case, bar what we consider here, horizontal position. If you consider a bar in vertical position, one end is fixed. Now the force acting on the bar due to self-weight at the CG. Now what is the deformation of bar due to self-weight? Delta L is equal to WL square by 2E. What is W? W is nothing but specific weight of a material. Specific weight means weight per unit volume. It is nothing but weight density. Density, we have three density. One is mass density, weight density, relative density. Now this is the weight density or specific weight per unit volume. That you can, I think, the density is studied in fluid mechanics, the properties of fluids.
Yes, sir.
Yeah, there are three different density they are discussed there.
Yes, sir.
Yeah, mass density, weight density,
Mass by
relative
volume.
density, right?
Density. Yes. Yes,
Yeah,
sir.
here specific weight is nothing but weight density. Here we consider a solid material.
Weight by
There we
gravity.
use a fluid material, means it may be liquid or gaseous phase. Okay. Next, after that, if we instead of self weight, the whatever the weight of the body is, self weight of the body is there, consider that as an external force acting on the bar. Deformation in the bar subjected to a force equal to self weight. Then what is the deformation bar is delta L is equal to WL square by E, right? Yeah. Now the previous slide we discussed about factor of safety, right? What is the factor of safety? It is the ratio of failure stress by all-over stress. Failure stress for ductile material considered as yield stress. For brittle material considered as ultimate stress. Now this is a formula you should remember for factor of safety for ductile material and brittle material. Next, for if you compound bars, a bar is made up of 2 or more materials, then it is called as a statically indeterminate member. When you say statically indeterminate member means if 2 unknowns are there, only 1 equations are there. Then how do you determine 2 unknowns? It becomes statically indeterminate. Then I will go for use one more formula. Now if a bar is subjected to a statically indeterminate or compound bars, then what are the formulas used? 2 formulas used. One is the vector sum of all the force equal to 0 or moment equal to 0. That is called as a equilibrium equation, force equilibrium or a moment equilibrium equation. That is the first formula. Second one, what is the elastic deformation equation? Equation based on geometric relation regarding elastic deformations. What is the elastic deformation? What is the deformation produced by first member? A first bar is equal to deformation induced in the second member. What is the deformation here? In general, it is for a uniform cross section means it is PL by AE, general formula. For first one, P1 L1 by A1 E1. For second member, P2 L2 by A2 E2. Again, before that, one more we will not discuss here. There is a principle of superposition theorem. That is also very important. Next, after that, we discussed about elastic constants. Elastic constants are the constant that tells the elastic behavior of engineering material within the elastic limit. There are 4 elastic constants are there. One is Young's modulus that we represent as E, shear modulus that we represent as G, bulk modulus that we represent as K, and Poisson ratio that is nu or mu. Both we can represent. Some textbook they use nu, some textbook they symbolically represent as mu. Now, first elastic constant is Young's modulus or modulus of elasticity. Modulus is nothing but what? Constant. Constant for elasticity. Our scientist name it is Young. Young is the scientist name. Young's modulus is a ratio of normal stress to the normal strain. Unit is Newton per mm square. Similarly, shear modulus or modulus of rigidity. It will not undergo any deformation. Right? That is shear stress to the shear strain. Shear stress is represented as tau, symbolically represented as tau. Shear strain is gamma. That is also unit is Newton per mm square. Yeah, then next slide is visible.
Yes, sir.
Yeah, now the next elastic constant is bulk modulus. How do you define bulk modulus? It is a ratio of spherical stress to the volumetric strain. Spherical stress is nothing but 3 mutually perpendicular stresses. 3 equal mutually perpendicular stresses means stress is acting along x direction, y direction, z direction also. Those 3 stresses are mutually perpendicular and they are same magnitude. Those stresses are called as spherical stresses. Once spherical stress is acting over the component, it changes its volume. Not only one dimension it changes, overall 3 dimension the component changes. That is the volumetric strain you will get. The bulk modulus is ratio of spherical stress to the volumetric strain. The unit is same. Unit is same, strain no unit, right? That is a Newton per mm square. Now what is volumetric strain is change in volume by original volume. And one more, this is not we'll discuss yet, we'll discuss in later 1 or 2 classes, complementary shear stresses, that we'll discuss later. Next, 14th problem, as you know that what is meant by Poisson ratio? It is a ratio of lateral strain to the longitudinal strain. Lateral strain will represent as epsilon lateral divided by longitudinal will represent epsilon longitudinal. Again, negative sign is there. Remember here, negative sign. What the negative sign shows here? As the length increases, lateral dimension increases. Longitudinal dimension increases. As the longitudinal dimension increases, what happened? Lateral dimension decreases. That's the negative sign indicates. As you know that for circular cross section of the rod, what will be the lateral strain here? Delta D by D. Longitudinal strain is delta L by L. Now problem number 50, sorry, the formula 15th equation it is generalized Hooke's law. In the previous slide we discussed only Hooke's law, that is a one dimensional. Stress is equal to E into epsilon, sigma is equal to E into epsilon, that is a one dimensional stress strain relationship. If you go for three dimensional stress strain relationship or strain stress relationship, then you go for apply generalized Hooke's law. That is how do you remember here? Now consider three coordinates x, y and z. If you want to write the what is the strain induced in the along x direction, in that direction the sigma x by E positive term will come. Other two direction, other two axes, Poisson ratio the term will come because the dimension decreases. See the sigma x is equal to, sorry, epsilon x is equal to sigma x by E minus mu into sigma y by E minus mu into sigma z by E. If you want to write for epsilon y is equal to minus mu into sigma x by E plus sigma y by E minus mu into sigma z by E. Similarly, you write for third one also. Remember this generalized Hooke's law. Now after that we discussed about relationship between elastic constants. First, what is the relation between shear modulus and Young's modulus or Young's modulus in terms of shear modulus? You can take that G is equal to E by 2 times of 1 plus mu. For bulk modulus and Young's modulus, it is K is equal to E by 3 times of 1 minus 2 times of nu. Relation between three elastic constants, Young's modulus, bulk modulus and shear modulus, E is equal to 9 kg by 3 times of K plus G, right? And also here in the bulk modulus volumetric strain, as you know that volumetric strain is a 3 times of linear strain or longitudinal strain. That volumetric strain is also the sum of the strain along the longitudinal direction, epsilon x plus epsilon y plus epsilon z. Now you can here itself will write below the bulk modulus itself you write this formula. Then last we discussed about thermal stresses due to rise in fall in temperature of a constrained body, then the thermal stresses are developed. Here three cases are there. One is free expansion. What is the deformation induced due to rise in temperature or fall in temperature of the body? Delta L is equal to alpha into delta T into L, where alpha is nothing but coefficient of thermal expansion, delta T is nothing but rise in temperature, that is T2 minus T1, L is the length of the member. Next, if it is a body is completely constrained or restrained, now thermal stresses are developed, that is sigma is equal to alpha into delta T into E in Newton per mm square. Now see the formula, free expansion and on the completely constrained. Free expansion deformation takes place, that is alpha into delta T into L will come here. For completely constrained, what is stresses are developed, sigma is equal to alpha into delta T same, E will come here, Young's modulus of the material will come. Next, partially constrained, there is a gap between one support to the free end of the surface of the member. Then you can remember that. That is what is the formula you should remember. Free expansion is equal to, due to rise in temperature, that is equal to restrained or mechanical deformation in the component. Then you go for simplify it. Finally, you get sigma is equal to alpha into delta T into E minus delta by L into E. Well, delta is nothing but what? Clearance or gap between the support and a free face of a member, right? Now see the free expansion is equal to restrained or mechanical deformation. Free expansion of a bar due to rising temperature it is alpha into delta T into L. Restrained or mechanical deformation it is PL by AE. And also one more here, P1 is equal to P2, that is a compound bar for thermal stresses, but that topic is not there, okay? And one more here, this is a very important sign convention. How do you remember sign convention? Always tensile forces, the forces acting away from the body are positive. The forces acting towards the body means compressive nature, those are negative. Negative force and positive force. Remember this sign convention. Okay. So still we have, I'll take about 15 minutes more. Once you revise this all the formulas, okay, we'll go for solve the problem. Okay, take notebook, pen and pencil. Now again I will go for take the question paper problem. So I will take the question paper problems. Okay, 1 minute. Yes, now PDF is visible.
Yes, sir.
2016 paper, December 2016 and January 2017. The paper is visible.
Yes, sir.
Okay. Now the first model, first question, 82 will not discuss here. We'll go for okay, 1 or 2 class required for that. I'll come to later that one. Now see that second question, model 1, second question. Write a note on constituent the law of anisotropic material. Again, this is not in your syllabus. Second 2b, because this scheme to scheme the syllabus has changed. If you go for previous scheme, the syllabus is entirely different from yours. Okay. See the second B, 2B, draw a stress strain diagram for ductile materials and mention the salient points. They asked how many mass? 4 mass. Now how much you want to write? So stress strain diagram for ductile material. Which is a ductile material to consider? Yes, give me response. Which is the ductile material consider here? Consider a low carbon steel or mild steel. Draw only a stress strain diagram. On the stress strain diagram, just represent A, B, C, D, E. What is a proportional limit? B, elastic limit. C, ultimate yield point. D, lower yield point. E, ultimate point. And F, failure point or breaking point. Only that much you represent here. See the question, read the question properly. Draw a stress strain diagram for ductile material. Any ductile material you can take and mention the salient points. Don't go for explain each term. Just mention only salient because they asked only for 4 marks. Read the question once or twice, understand it, then see the marks. If you suppose the same question they may ask for 6 to 8 marks, then what you will do? Write the stress strain diagram, represent the salient point, then at least 3 to 4 salient point you should explain it. Means you should define it. Okay, then out of 4 you will not expect 4 marks. You expect only 3. They will deduct 1 mark. Okay, depend upon your sketch. If a sketch is not right, okay, representation is not right, your sentence or the statement is not so. If you wrong means they will deduct 1 mark. Okay, now what is second 2C? Now we'll copy this question. Yes, all of you copy this question. What is the question here? A composite bar is shown in figure. Determine the stresses developed in each member. Take E suffix Al. E stands for Young's modulus. Al stands for what? Aluminium. Is 0.07 into 10 to the power of 5 Newton per mm square. Newton per mm square. Okay, next E suffix steel. E suffix steel. Young's modulus for steel it is 2 into 10 to the power of 5 Newton per mm square. Again they ask for 8 marks. Now see the diagram. One portion is aluminium. Its cross-sectional area is 1000 millimeter square. Length is how much? 0.1 meter. And is given AB portion. Now BC portion cross-sectional area is 1500 millimeter square. Again is made up of steel and the length is 0.15 meter. At both end is constrained. Then it is a load is at the junction of aluminium and steel. A load is occurred here 200 kilonewton acting toward right direction. Right? Yes. Now copy the question. The same question also appeared in the previous. In the last 15 days, again the back subject for the same subject, the same question also appeared here. Now this question appeared twice. Yes, all of you have taken the question. Better write in A4 sheet that I will consider as assignment also. And 2 more problem I will give for assignment. Total 5 questions are there in the assignment 1. You write it and then you send it. If you try to solve here itself means the same copy you can attach there. Yes, all of you copied the question. Just give me response.
Just a second, sir. 1 minute.
Either copied in the A4 sheets or notebook. First you copy the question, then write the given data. Then you go for solve the problem. I think this same type of problem is solved, right? But only the dimensions and the loading properties changes here. Just you copied the question.
Yes, sir. Done, sir.
Okay. Now take a solution, write the given data and call it as the aluminum portion is portion 1 and the steel it is portion 2. Now how do you solve this problem? Then write the given data, Young's modulus for aluminum and Young's modulus for steel. Now how do you solve this problem? Yeah, what is the approach?
Equilibrium condition. First,
This is what type of bar it is?
compound.
Compound bar. And also it is a statically indeterminate member. How do you say it is statically indeterminate member?
Equilibrium condition.
Yeah, at the junction, load is occurred here. Now at the both end, it is support here. See that at this, due to external applied load 200 kilonewton here at the junction, at the support A, at the support A, what will be the reaction is opposite to the applied load. I think that arrow mark is visible. Just give me
Yes, sir. 200 kilonewton.
Yeah, 200 kilonewton is external applied load. This is not 200. If you be careful, it is. If you write 200 means it's wrong. Now take it. This is a P suffix 1 or P suffix 1 you take. That is not a 200 kilonewton. Be careful that. At the same time, if your 200 kilonewton is applied here at the junction, at the support C, at support C, what will be the reaction force here? Reaction force acting away or towards here? Sorry, away or towards the body? Reaction force act towards the body, right? Yes or no? Then called as that is that force you called as 2. Yes, are you following or not? Yes, give me response.
Yes, sir. Following.
Yeah. Now how many unknowns are there? P1, P2 are unknowns. 2 unknowns are there. We have only one equation. What is that equation? Vector sum of all the force acting in horizontal direction is equal to 0. What is the one more equation? Now remember the statically indeterminate or compound bars. We have, remember those two equations. One is by applying a static force equilibrium equation. Second one is, what is the second one is? Yes, anybody can give the answer.
Elastic.
What is the second equation we used in statically indeterminate member or compound bars? Yes, I'll move over that list of formulas.
PL delta
Yeah,
L
it's statically
is equals to
indeterminate
delta
motor.
L2.
Yeah, one is by applying vector sum of all the force equal to 0 horizontal direction. Second one is elastic deformation equation. Delta L1 is equal to
Delta
delta
L2.
L2. That is your approach, right? Means,
Yes.
yeah, now called as this is the portion 1. Now called as this is the portion 1. Now this one you called as portion 2. Okay, portion 1 and portion 2. Aluminum is a portion 1, steel is a portion 2, right? Now write the first equilibrium equation. What's the first equilibrium equation? The vector sum of, I think here I can't write that. So symbol is not highlighting here. Okay. Now first write the first equation. Vector sum of all the force horizontal direction is equal to 0. What is the sign convention used? The forces acting towards right direction is positive. Towards left direction it is negative, consider. That is, so what you will get? If you apply vector sum of all the force in horizontal direction equal to 0, P1 is acting plus P1 or minus P1 it is acting towards left, minus P1 plus how much here at the junction 200 kilonewton, 2 into 10 raised to power of 3, 10 raised to power of 10 raised, 10 raised to power of 3, that is positive, right? Acting towards right side direction, plus or minus minus P3, that is equal to 0. If you apply vector sum of all the force acting in horizontal direction is equal to 0, then you'll get the equation. Now Carter, this is equation number. Now finally what you get? Finally what you will get? Plus P2 is equal to
Is equals to
200
200 into 10 raised power 3.
into 10 raised to power of 3 you will get, right? Now Carter, that is equation
Sir,
number 1. Yes?
sir, are you typing and trying to show us, sir?
Yeah, I'm
It's not
typing.
visible.
It's not visible. Okay. Okay, 1 minute now. Then now it is visible.
No, sir. No.
No. Okay. So anyway, you are calculating, right?
Yes,
We'll
sir.
check it. P1 plus P2 is equal to 200 into 10 raised to power of 3 Newton. Called as equation number 1. Right? Yes, all of you got that?
Yes.
Yeah, what is the second equation you used? The deformation in portion 1 is equal to deformation in portion 2. Right? The second unit is compound bar or
Yes.
statically indeterminate member. Deformation in portion 1 is equal to deformation in portion 2. I think use this formula. Delta L1 is equal to delta L2. Again, delta L1, what is the formula used? Throughout the length, the cross-sectional area is same, right? For portion 1, aluminum portion. Second also throughout the length, the cross-sectional area is same. Now we'll go for apply. General formula for straight bar. What is the deformation straight bar is? General formula is PL by AE. Here are two portions are there. For first portion, P1 L1 by A1 E1. That is equal to
E2.
P2 L2 by A2 E2. Now apply this formula. I think this is on the screen, it is visible. Yes, in the list of
No,
formula it's shown here. In the list of formula, 11th equation, I'm showing here. Is it visible?
No, sir. The last slide only is visible. The exam paper.
Exam paper you are viewing. Okay, okay. So I think I'm not sharing that. Yeah, sorry. Okay, it's a mistake in my side. I'm not shared the screen. That's why you're not able to see that. Okay. Now tell me, man, now the slide is visible. The problem P1 plus P2 is equal to
Yes, sir.
210 to the power. Yeah. There is the first one over. Next, we'll go for apply second equilibrium equation. Delta L1 is equal to delta L2. Yes, delta L1 is equal to delta L2, right? Substitute delta L1 is what? P1 L1 by A1 E1, that is equal to P2 L, delta L2 is nothing but P2 A2, P2 L2 by A2 E2. Now check, P1 P2 are unknown, as it is it take P1 into L1 is how much? 0.1 meter is given, convert into millimeter, dimension you should take millimeter, 0.1 into 10 to the power of 3, whole divided by A1 is for aluminum first portion 1000 millimeters square into E1, Young's modulus of aluminum it is 0.7 into 10 to the power of 5, that is equal to P2 is unknown, L2 0.15 meter turned into millimeter, 0.15 into 10 to the power of 3 whole divided by A2 is how much? 1500 into E2 is how much? Nothing but Young's modulus of the steel 2 into 10 to the power of 5. Now we will get, finally we will get P1 in terms of P2. Am I right? Now tell me what is the P1 is equal to how many times of P2? So now who will give the answer? We have only 12 minutes time. So be fast. Now once you get P1 in terms of P2, substitute into the equation number 1. Now we'll get P1 and P2 will get, then substitute that P2 into P1 will get. Now what is our aim? Determine the stresses induced in each bar. What is the stresses? Sigma is equal to P1 by A1 for the first portion. Second portion, sigma 2 is equal to P2 by A2. Yes. What is the value got? P1 is equal to in terms of P2. Yes, Hitasha. Sorry.
Sir,
Sir,
P1 is equal to 107.75 into 10 power 3 Newton.
107.75
Kilonewton.
10 to the power of 3.
Newton.
Terms of P or terms of P2 or is value of P1 it is? Sorry, I'm not audible, ma. Is anybody? Okay, unmute yourself. So mute yourself
Sir, without P2.
without P2. This is only new. Okay, P1 it is.
Yes, sir.
Yeah, what is the value of P2?
307.75 into 10 power 3 Newton.
307.75
0.75 into 10 power 3 Newton.
power of 3 Newton. Yes, these two are right answer. So actually P1 is plus, P2 will get negative value, I think. Am I right? Is it right? Yes, someone has to give me response. P2 will not get that much value, ma'am. Is any other answers are there? Yes. So both value you got P1, P2 you got positive value. Is any other answers? We have still
15, sir.
Yes.
82.15.
Sorry,
82.15.
which one?
P2, sir.
P2 82 point.
15.
What about P1?
No, sir. Wait, sir.
You calculate. So whenever you got the answer P1, P2 value, check whether it is right or wrong. How do you check whether right or wrong? The summation of those two will get 200 into 10 raised to the power of 3 Newton only you should get. Then only your answer is right. Otherwise your answer is wrong. Whenever the
Yes, sir.
values answers you got, verify it whether it is right or wrong. Yes. What is the value of P1? Yes, give me the response. Give me the answer. Yes, Aradhana, Grishma.
Yes, sir. Checking, sir.
Are you calculating or voice is not audible? Aradhana,
Solving, sir.
still you are solving. Okay, Grishma.
Sir, I only said that solving.
You only told that answer.
Oh, sir, I'm solving still.
Still you are solving. Okay. Istar Rani. Yes, yes.
Sir, in
Geeta
terms of P1,
Sir,
can you say the
solving,
answer,
sir.
sir?
First, okay, delta L1 is equal to delta L2. If you go for this equation number 2, if we take equation number 2,
Hmm.
okay, 1 minute. This is if you go for the equation number 2. Now that will give in terms of what? P1 in terms of P2 you will get.
Yeah, sir,
Okay.
P1 in terms of P2.
P2 you will get. After
0.35
that,
into P2.
substitute that P1 in terms of P2 into equation number 1. Because then equation 1 and 2, if you solve that equation 2, now 2 unknowns are there, 2 equations are there. Now either go for directly use the calculator or you substitute P1 in terms of P2 into equation 1, then solve it. Now tell me final answer.
P1,
Yes. Yeah, P1. Now what you
140.
can see on the screen, those answers are not right. Those answers may be wrong. Now tell me once you calculated, now tell me your answer. Now we'll judge whether your answer is right or wrong. Yes. Yes,
P1
go ahead.
1.85 into 10 power 3.
Sorry, 1.85.
51.85 into 10 power 3.
Sorry, it did.
51.85
Okay.
into 10 power 3.
Okay.
P140 10 power 3.
Okay.
P2 1.
Yes, P2 value how much you got?
148.148 into 10 power 3.
1 minute. 148 point
148 into 10 power
148 into 3.
10 raised to power of 3. If you add those two, you'll get 200 into 10 raised to power of 3. And then you make it here. Instead of 148, round off into second 148.15, right? Now it's if you add those two, you'll get 200, right? Yes or no? Then your
Yes,
answer is P1. Once you calculate P1 and P2. Now you calculate sigma 1. What is sigma 1? What is the formula used sigma 1? What is the general formula for the stress? Sigma is equal to general formula sigma is equal to force by area. For first portion, sigma 1 is equal to P1 by A1. For second portion, sigma 2 is equal to P2 by A2. Now tell me what is the value of sigma 1 and sigma 2. Yes, now we will give the answer. We'll check. Still we have 3 minutes time.
sigma 1 61.85, sir.
1 minute. Sigma 1 is equal to 61.85.
61.
What is the unit? Sorry. Newton per mm square.
Sir, 51, sir.
Exact 61 you got?
51.85.
51.83. Sorry, 51.83. Am I right?
85.
Is it right, ma? Is it visible?
it's visible, sir. That is 51.85.
85. Okay, no problem. Depend upon that, how many
No.
digits you consider after decimal. If you
However, I
want to
got
get
94,
exact
sir.
value after decimal, minimum 3 digit is considered.
Oh,
Okay.
I got 51.94, sir.
Okay, no
No
problem.
problem.
After decimal,
Okay.
no problem. Sigma 2 first stresses acting in second portion for steel. Area is more and load also more, right?
98.76.
98.76.
98.76. Okay, good. Yes, thank you. Thank you for attending this class. No time over. Still 1 minute is there. Okay, I will send the assignment. Total 5 questions are there in the assignment. Write it in A4 sheets and send me that. Whenever you are completed. Okay, within last time for sending the assignment is before the internal. Okay. Okay, when you have internal first in the 8th, I think 7th you should submit. Okay. Yes. Thank you. Thank you for attending the class. Now I'm leaving the session. Or if you have any doubts, you can clarify your doubts. Any doubts is there? Okay. Thank you. Thank you one and all. I'm leaving the meeting. Okay. Yes. I need a response from your side.
Okay,
Yes,
sir.
Okay. Thank you. Thank you one and all.